Hi, my name is Zishan and my group mate's name is Simra. This project is about water segmentation in videos. We want to find water in videos which are captured by still cameras, a single still camera. Um, so we can see that here we have an input video of water acquired by a single still camera, and we want to basically be able to identify regions of water versus non-water, and we can find applications of this kind of technique in floodwater detection on streets, or finding water spills in inaccessible locations like basements. So conventional approach to solve this kind of a problem would be to uh, perform a classification along with localization. So find the object of interest, which is water in this case, and then localize it by using bounding box, which might not be the best approach in this kind of problem, because we want to identify the exact location of water and non-water regions in videos or images. So here we have an example of instance segmentation, and we can see that what we want is basically identify every pixel as water or non-water. So the example here shows every pixel as being marked as dog or cat versus background. Um, so that's what we want, and one of the existing approach that has been taken is what's called a fully convolutional network, in which basically you have all of the layers as your convolutional layers, and there's no fully connected layers. So our approach will be very similar to this. And so in order to briefly explain that, a convolutional network has these convolutional layers after the input image, and then as you go forward, you have these fully connected layers at the end. However, in a fully convolutional network, you have all of the layers as your convolutional layers as you go forward, and at the end, you have like a coarse segmentation of the input image or video. So that's what we want, and that's what we shall do. We can see here that the network architecture we're using is somewhat similar to AlexNet, because that's what our architecture is inspired from. We basically converted an AlexNet into a fully convolutional network, but not precisely so. Our network is not exactly similar to AlexNet, but it's inspired by it. We basically initialize the first. We keep the first few layers as fixed. We only train the last two layers. The number of parameters that we have to train is around 4,000. And the reason why we only train the last few layers is because we do not have a lot of training data. So we only train the last few layers. We initialize the first few layers with the weights obtained from AlexNet, and the last layers is initialized with random weights. So the data loader that we have a total of 60 training videos, and we wrote our own data loader where we basically break every video into a number of snapshots, 10 frames per video. So we take 10 frames per video and we bunch them as a single batch of input. We normalize the batch, and then that constitutes a single input data set, a single batch of input data set. When we train the network, we can see that both the training loss and the test loss is going down. The training loss that we are using here, the loss function is negative log likelihood computed over each pixel and then averaged over all the pixels. And we can see that both losses are going down, which kind of indicates that we are actually performing a very good training here, and we're not overfitting or underfitting. We're actually learning some useful parameters. So this is an example, specific test examples here, where we have different scenarios of water in videos, and the second column shows here ground truth, and the third column shows here our prediction. And we can see that we have pretty decent accuracy of finding the ground truth. And the true positives and true negatives are, for the first video is around 98% and 93% respectively, and for the second video is 99% and 86% respectively, which is pretty decent. We also perform some more comprehensive test experiments. We have a total of 30 test videos, so we computed the true positives and true negatives over all the test videos as a function of our training, and we can see that both are following a generally upward trends, which basically tells that we are learning some useful parameters here, and our accuracy is improving on the testing set. Overall, we have 97% true positives and 81% true negatives. So we have 3% false positives and 19% false negatives. We're generally doing better on water region than non-water region, and that is because we think probably because we have more water in the videos versus non-water, and that's why we have slightly better performance in water region. Our conclusion is that we're able to segment water with decent accuracy, and we can further improve the results by incorporating maybe a memory element or using a prior model for the output prediction to get rid of the isolated water or non-water regions. And finally, we can put an upsampling layer to improve the end resolution of the output segmentation, but that would require more training data. That's all for now. Thank you so much for your attention.